Okay, today I'm going to talk about the maximum Bochner Riesz operator in the plane. And my name is Shukun Wu, and this is a joint work with Xiaochun Li. And now let's get started. First, let's recall some notation. And the Bochner Riesz operator T lambda Tfx is defined to be the integral in the plane R2, where the integrand is f hat, the Fourier transform of f times a special function 1 minus c squared over t squared, the whole thing's to the power of lambda, and we're taking the positive part here. And also we times the character e to the x dot c. And this is basically defined Bochner Riesz operator. And the associated maximal operator T lambda star f is defined to be the supreme of all T lambda Tf. And in the supreme, we're taking all those T greater than 0. Okay, and here's a little remark. When lambda equal to 0, so basically when lambda equal to 0 here, the Bochner Riesz operator of order 0, especially the Fourier inverse or the partial sum of the Fourier inverse, because we are restricted the integral inside the region C less equal than T. So it's a ball of radius T. Yeah. Because of that, the Bochner Riesz problem is really closely related to the Fourier inverse or the inverse of Fourier transform, and as a result, it's also closely related to the pointwise convergence phenomena of Fourier inverse. Okay, and the goal of our paper is to answer this following question. So basically, when does this partial sum converges to a constant c times fx? Yeah, and here we assume f is a LP function. So basically, we would like to ask for what p and lambda the pointwise problem star is true. Okay, and when p greater than 0, the problem star is, so the pointwise convergence problem is well known, and is a work by Cabré, Ruby Differentia, and Vega, if I remember correctly. And the work is like 30 years ago in 1985. Well, but on the other hand, when p is less equal than 2, the problem is still open, because by Stein's maximum principle, the pointwise problem is equivalent to the weak LP boundedness of the maximal operator T lambda star here. Yeah, so so when p less equal than 2, it's actually widely open. Only few results are known so far. Okay, so our result is that we prove the maximal operator is bound in LP space when lambda is greater than the lower bound here, which is a really strange factor. To help you digest this factor, here's a graph. So in this graph, let me see. There's a point 1/2 on the top, and 1/2 at the bottom. So this axis is the lambda axis, and this axis is the 1 over p axis. And there are 3 points here actually, which is 2/3, 7 over 10, and 13 over 18. And for some special point here, which is the point when these two terms are equal. And we connect this point with the point here using a straight line, and we also connect the point with the point here using another straight line. Then the region C here is what Tao obtained for the boundness of the maximal operator T lambda star in his paper in 2002. And the yellow shaded region here, the yellow shaded region here is our small improvement in our paper. And the region A here is proved to be false for the boundness of the maximal operator. And as you can see, there's still a really big region B here, which is the remaining part. And we don't know what's going on basically in the region B, and it's still open. Yeah. Okay. So as I mentioned before, our goal is to prove the LP boundness, the maximal operator is bounded in LP space. So basically we want to prove that the LP norm of T lambda star F is bounded by the LP norm of F. There are actually 3 standard reduction. The first one is that we reduce the study of the maximal operator to another maximal operator S star. So S star is defined to be the supreme of all SF xt. And the function SF is defined to be the integral of the character times the Fourier transform of F times another special function phi here. And inside phi is a smooth function, and basically we can think of it as the smooth cutoff of this annulus of thickness delta and radius 1. Okay. Now, to prove the desired estimate here, it suffices to prove that the LP norm of the function SF star here is bounded by the LP norm of F times a factor of delta to the negative lambda power. Okay, this is our first reduction. Oops. And in the second reduction, we claim that it suffices to work on the time interval, compact time interval 1, 2. So basically, if we define another maximal operator S star tilde F as the supreme of SF inside a smaller region 1, 2, and this result is proved by Tao that we only need to prove this LP estimate so that we can obtain the global one, which we label red star here. Okay. And the third reduction is it suffices to assume the function F is contained in an arbitrary delta inverse ball in the plane. And we only need to prove that LP of S tilde star F taking integral inside the ball set of radius delta to the -1 center at the origin. And this quantity is bounded by the LP norm of F times the same factor with an additional power P. Okay. Yeah, this is our 3 reduction, and we only need to work on this estimate here. Recall that the supreme operator S S star theta is defined as this. And we are going to prove a restricted weak LP estimate. So by real interpolations, we can get all those strong L2 LP estimate. So here we assume F is a indicator function of a set E, where the set E is contained in the delta inverse ball, which is also the support of F. Yeah, so basically the set E is any set containing any delta inverse ball in the plane. And now we are going to divide the set E into the union of E1 and E2, where E2 is a union of dyadic is a union of dyadic family of maximum is the family of maximum dyadic cubes, such that the contribution of E, the original set E inside the cube, is pretty large. And here beta 2 is a factor that we will choose later. Okay, so now we can partition our original function into two parts. Here, in the first one, we restrict it to the function to the set E1, and the second part we restrict it to the set E2. Okay, and yeah, now let us just denote the indicator function of E1 as F. So the Fourier transform of SF, the xt Fourier transform of SF, after several calculations, we observed that it is roughly contained in this region, which is the unit ball in R2 space across the interval of length R in R1 space. So this is a subset of R3. And as a result, by the locally constant property, SF is morally constant inside the region B cross I, where B is any ball of radius 1 in the plane, and I is any interval of length delta. And because of that, we can use this locally constant property to morally bound this function as the sum of SFXTJ times a cutoff of a set Fj here. So the Fj has the property that all those set Fj, J from 1 to R, they are mutually disjoint. And Tj is just a point 1 plus J time plus delta. So basically we partitioning the time interval 1, 2 into delta to the minus 1 smaller intervals, and Tj just the endpoint of each of the smaller interval. Okay. As a result, to prove the LP estimate for the maximal operator, I should have tilde here, as tilde F, we only need to work on the reduced function, which is SFTJ times Fj and some orders J. Okay. Now, for each J, we calculate the Fourier transform of this function, and we find out that it's actually supported in the annulus of radius Tj and thickness delta. So we are going to partitioning this annulus into rectangles here. So yeah, so each of this rectangle has dimension delta times delta half, and we do wave packet decomposition in the really classical way. So the right hand side here is a wave packet decomposition, and Vs is a L2 normalized function, and a little remark here is Vs, the Fourier transform Vx is supported in any of this interval. This rectangle of delta of dimension delta times delta half, and Vs, yeah, the support of V hat. And Vs is morally supported in a dual rectangle of radius delta to the negative half times delta inverse. We denote this by Rs. Okay. So after further reduction using wave packet decomposition, the target operator become the right-hand side here. This one. Now we are going to make a further decomposition on this model operator. We define two collection of wave packets, B1 and B2. So B1 contains all those wave packets whose magnitude is small, and B2 is basically the negation of B1. And here beta 1 is also another factor we will choose later, like beta 2 we introduced before. So we end up with our final decomposition. We decompose S star F into the sum of two other functions, T1F plus T2F. And for inside TKF, this function, we're summing all those wave packets belongs to the collection BK here. Okay. For T1F, we are going to work in L6 space. So the L6 norm of T1F is actually equals to this part. Here, we already used the fact that the set Fj are mutually disjoint. Yeah, so we can, because of that, we can take the summation outside. And by the L6 decoupling, which should credit to Bourgain-Demeter, we can bound the right-hand side as this quantity here. Okay. So here omega is can be think of as a directional vector. So inside the summation here, we're summing all those wave packets whose direction is omega. So by the saying wave packet has direction omega, it means that the Fourier support of Vs is contained in a rectangular cap whose shortest side is pointing to the direction omega, as shown here. As a result, we further can bound the above quantity by this one, and this is because when the direction omega is fixed here, the sum inside the summation of inside this sum of wave packets, the function Vs, the support of function Vs, are morally disjoint. So we can take the sum outside and end up with the expression here. Okay. Now let's recall that in the collection B1, we have the magnitude of the wave packet is pretty small, and it's bounded by some factor beta 1. So we can basically move 4 of its power in this 6 using beta 1 and left the remaining 2 as this. And this is basically an L2 estimate. So we end up with basically T1F, the L6 norm of T1F is bounded by the right hand side, which is an L2 estimate. Okay. For T2F, we have we basically put an absolute value inside to have this desired bound here. And because in B2, those wave packet, the magnitude of those wave packet is big. So we borrow 1 magnitude, and at a cost of beta, beta 1 to the minus 1, we gain 1 more power here, which make the right hand side looks like L2 norm. And also we use the locally constant property of the function Vs, so that the right hand side is morally the indicator function of Fj union the support the rectangle Rs, and this is equal to the following. So and the kernel Kxy is defined to be this pretty complicated expression. So we can prove what our want here if we can estimate the kernel, the integral of the kernel with respect to y has the upper bound beta 2 times delta to the -1. In order to prove this estimate, we will use the information of E2. So basically the support condition of E2, and also we find that in the expression of Kxy, when the point X is fixed, all those wave packets that make contributions actually would actually form into a bushes whose center contains the point X. And because of that, the magnitude of Kxy really depends on the distance between X and Y. So use these 2 information, we are able to prove the desired estimate star. Okay, now we are really close to conclude our proof. So we recall that we actually break our original function into 3 parts. The first part is S star tilde F times E2, composed with the indicator function of E2 plus T1 1 E1 plus T2 1 E2. And we estimate this term in L6 space, and we estimate this term in L1 space. And we are going to finally estimate this one in L2 space. And to do this, we will use a local L2 estimate. So that combining with the information that E2 is a union of dyadic cube, such that the density of the original set on Q is pretty large. Again, it's bigger than beta 2 Q. Yeah. We can end up with the L2 norm of the first part. Well, is in fact bounded by delta half beta 2 to negative half times the magnitude of E. And because of that, we combine, well, let's see, combine this first estimate. This is the first estimate. And yeah, this is the second estimate. And this is the third estimate. Combine 1, 2, 3, 2, so that we end up with the L. Let me see, what's the factor here? I guess it's 18 over 13 is bounded by delta to the, let's see, or maybe I should write the LP norm of this is bounded by delta to the wait, let me check what's the exact factor here. Yeah, oh, let's do it in this way. So the L 18 over 13 norm is bounded by, well, actually no, sorry, I messed up a little bit here. The L2 norm of this, actually weak L2 norm is bounded by delta to the phi over 18 times the measure of E to the 13 over 18 power 18. And this estimate would be enough to prove the weak LP estimate, I guess. 18 over 13 delta to the, I guess, 9 over 2. 13 over 18. This is the restricted with time estimate we want. I'm not sure the power I gave here is correct, but yeah, basically this is our strategy to prove the our result. Thank you for your time. And that's it.